Hello my friends and welcome back to the Today Machine channel. The creation of a marine propeller pattern is a process that involves multiple stages to ensure precision and quality. These patterns are essential in the foundry process, where they are used to mold sand and cast the final propellers in stainless steel. The process begins with detailed measurements provided by an engineer. These measurements are critical as they include allowances for machining, shrinkage, and contraction that occur during casting. A full-sized layout of the pattern is then created, serving as a reference throughout the pattern-making process. This layout includes sections and measurements taken at specific intervals. One key element in the layout is the creation of slices, called cants. The cants form the various sections of the propeller and must be prepared with precision. A hole is drilled in the center of the hub, which serves as a crucial reference point for all subsequent measurements. This hole is also used by the foundry to set up the pattern during the casting process. The cants are then glued together, pivoting around the central hub. The degree of offset between the cants is determined by the pitch of the propeller blade. Once assembled, the steps created by the cants are carefully smoothed to form a seamless blade surface. The forward and aft sections of the hub are prepared separately. The forward end is secured to ensure it is perfectly perpendicular to the hole in the hub, establishing a reliable reference point. Holes are drilled into the pattern as additional reference points for accurate measurements. As the shaping progresses, the blade face is meticulously smoothed and measured continuously to maintain precision. Dowels are added at specific points to gauge blade thickness, and excess material is removed accordingly. The aft end of the hub is then attached, and the hub is shaped to its final barrel-like form. The blade roots are shaped, and body filler is used to create a smooth fillet between the blade and the hub. Finally, several coats of pattern coating are applied to the finished patterns, containing additives that prevent foundry sand from sticking. The finished product is now ready for shipment to the foundry, where it will be used to cast the final propeller. The production of the world's largest ship propellers is a labor-intensive process, steeped in a blend of tradition and advanced engineering. Strategically leveraging local foundry expertise, the process begins with heavy metal casting using specialized bronze alloys, predominantly a copper-aluminum-nickel mix. These alloys are chosen for their durability and performance in maritime environments. The journey to craft a single propeller spans 3 to 4 months. The process starts with the creation of an inverted mold, a cavity that will form the propeller's shape. For the largest propellers, up to 300 tons of quartz sand mixture is utilized to construct this mold, enveloping a wooden model of the propeller. Once the mold is prepared, the casting process commences. The molten alloy is poured into the mold under the strict supervision of a casting supervisor. The entire casting operation is conducted in near silence to ensure precision, as the molten metal solidifies within a critical 10-minute window. After casting, the propeller remains encased in the mold for about a week before it is unearthed, allowing the metal to cool and settle. This is followed by several weeks of detailed inspection and finishing, ensuring the propeller meets rigorous standards before being deemed ready for shipment. Throughout this process, each specialist contributes their expertise, embodying a culture of pride and humility. Their collective effort ensures that these massive, intricately crafted propellers, essential to the global shipping industry, are produced with unmatched quality and precision. The installation of a large MMG propeller on a 1700 TEU container ship, such as the one built at Wenchong Shipyard in Guangzhou, China, is a complex and precise operation requiring meticulous planning and the use of an indoor crane. The propeller in question, manufactured in Germany, has a diameter of 6.5 meters and a mass of 28.5 tons. It is designed to be installed on the propeller shaft of the ship's main engine, A7S60MCC, with an output of 16,000 kilowatts at 105 RPM. Preparation. Before lifting, the propeller is inspected for any defects, and the installation area is cleared and prepared. The propeller shaft is aligned and thoroughly cleaned to ensure a perfect fit. Lifting process. The indoor crane, which is equipped with a heavy-duty lifting mechanism, is prepared for the operation. Slings and shackles are attached to the propeller's lifting points, ensuring the load is evenly distributed. The crane operator, working in coordination with ground personnel, carefully lifts the propeller. Extreme caution is taken to avoid any swinging or uncontrolled movements during the lift, which could cause damage or misalignment. Positioning and installation. Once lifted, the propeller is slowly and precisely maneuvered into position. The crane operator, with the help of spotters, aligns the propeller with the propeller shaft. The propeller is then gently lowered onto the shaft, where it is seated and secured. The installation involves aligning the keyway on the propeller with the corresponding slot on the shaft, ensuring a snug fit. Bolts are then used to secure the propeller to the shaft, and torque is applied according to the manufacturer's specifications. Final checks. After installation, alignment checks are conducted to ensure that the propeller is properly installed. The system is then tested for functionality before the ship's final launch preparations. In this section, let's find out how the Azipod propulsion units are assembled and follow their journey from factory to installation. The Azipod propulsion unit is a groundbreaking innovation in marine technology, transforming the way vessels are powered and maneuvered. The Azipod system is a gearless, steerable propulsion system where the electric drive motor is housed within a pod outside the ship's hull. This unique design allows the Azipod unit to rotate 360 degrees, significantly enhancing a vessel's maneuverability and operational efficiency. One of the most notable advantages of the Azipod system is its ability to reduce fuel consumption by up to 20% compared to conventional shaftline systems, making it an eco-friendly choice for marine propulsion. Since its inception 3 decades ago, the Azipod propulsion system has become a market leader in global shipping. Its superior performance, efficiency, sustainability, and reliability have revolutionized marine transport. The system is designed for optimal reliability and can be equipped with various levels of redundancy, such as double winding and redundant steering systems. This ensures safe operation even in challenging conditions. Furthermore, the maneuverability of Azipod units allows vessels to perform collision avoidance maneuvers more effectively and reduces the time required for a crash stop by up to 50%. The Azipod system is fully compatible with multiple energy sources, integrating seamlessly with the vessel's power systems. Its gearless design minimizes mechanical losses and contributes to a reduction in engine noise and vibration, providing a more comfortable experience for passengers and crew. Moreover, by locating the motor outside the hull, the system saves valuable space, allowing for more flexible ship design and reducing installation costs by up to 20%. The construction of the USS Gerald R. Ford, the world's most advanced supercarrier, stands as a remarkable achievement in naval engineering. Measuring over 1,100 feet in length and weighing 112,000 tons, this state-of-the-art vessel is capable of launching hundreds of airstrikes daily from its 2 expansive runways. Designed to house more than 4,000 sailors and Marines, the ship's cutting-edge technology makes it virtually undetectable to enemy radar. Named after the 38th President of the United States, the USS Gerald R. Ford, CVN-78, symbolizes the strength and innovation of the U.S. Navy. The construction process was a complex endeavor, beginning with the initial steel cutting for the ship's structure and culminating in the assembly of its nearly 500 modular components, known as superlifts. Each superlift was meticulously integrated, gradually bringing the massive vessel closer to completion. The assembly of the carrier involved significant milestones, such as the installation of the critical lower bow section and the final integration of the ship's island. The propulsion system was a key focus, with the installation of 4 massive bronze propellers, each weighing 30 tons. These components were crucial to the ship's performance, requiring extensive underwater work to ensure their proper function. Following the installation of the propellers, the dry dock was flooded to test the seawater systems, a pivotal moment in the ship's construction. As construction progressed, the ship underwent rigorous testing and adjustments to meet the exacting standards of the U.S. Navy. Despite challenges such as budget overruns and delays, the dedication of the shipbuilders and engineers ensured that the USS Gerald R. Ford would emerge as a powerful addition to the naval fleet. The christening of the USS Gerald R. Ford marked the culmination of years of effort and innovation. With its unparalleled capabilities, including advanced radar systems and enhanced operational efficiency, the supercarrier represents a new era in naval warfare. Launching a large vessel like the Hansa Australia, a 3,600 TEU container ship built at Shanghai Shipyard on Chongming Island, involves a well-coordinated process. The ship, with its impressive dimensions, 239 meters in length, 32.20 meters in breadth, and a depth of 19.20 meters, presents significant challenges, especially considering its launching weight of approximately 15,000 tons. Here are key notes to consider during the launching process. Before the launch, detailed planning is crucial. This includes assessing the tidal conditions to ensure optimal water levels for a smooth launch. The launch should coincide with high tide, providing sufficient water depth for the ship to float freely once it leaves the slipway. Additionally, precise calculations are required to determine the vessel's center of gravity, stability, and the forces acting on the hull during the launch. Given the size and weight of the Hansa Australia, the shipyard must ensure that the vessel's structural integrity is uncompromised during the launch. This involves reinforcing the hull and critical areas of the ship that will bear the brunt of the forces during the slide into the water. Safety measures must be in place for the personnel involved, including clear communication, emergency protocols, and the use of protective gear. The traditional method of launching ships, known as the side launch or end launch, would be applicable here. Given the ship's dimensions and weight, an end launch might be preferred, where the ship slides stern first into the water. The slipway must be carefully lubricated to reduce friction, and the movement must be controlled to prevent damage to the hull. Once the Hansa Australia is afloat, immediate checks are necessary to ensure the ship's stability and that there are no leaks or structural issues. The ship is then towed to a fitting-out berth, where final construction activities such as installing the superstructure, outfitting, and conducting sea trials will take place. Launching a vessel of this magnitude must also consider environmental impacts. Measures should be in place to minimize disruptions to the marine environment, and waste management protocols must be strictly followed during the launch. Successfully launching the Hansa Australia marks a significant milestone in its construction, requiring precision, coordination, and adherence to safety and environmental standards. The manufacturing process of propellers. The journey begins in the wax room, where wax pellets are injected into aluminum tooling using a press. Aluminum is chosen for its high thermal conductivity, which allows the wax to solidify quickly. The wax injection process is carefully controlled with water-cooled platens to maintain consistent temperatures, ensuring the wax forms correctly. The wax model, or pattern, is then assembled by welding the blades onto the hub using a soldering iron, followed by precise application of an automotive-grade goop to create the root radius. After assembly, the wax model undergoes cleaning to remove any lubricants used during the molding process. Next, the wax model enters the dip room, where it is coated in a series of refractory slurries and silica sands to form a ceramic shell. The first few coats are made from a high zirconia material, which provides strength and heat resistance. The model is dipped, dried, and coated repeatedly until a thick, durable ceramic shell is formed. This shell will later serve as the mold for the molten metal. Once the ceramic shell is ready, the wax is melted out in an autoclave, leaving a hollow cavity inside the ceramic mold. The mold is then baked at 1,800 degrees Fahrenheit to cure the ceramic and prepare it for the metal pouring stage. The molten metal, typically a 15:5 stainless steel alloy containing 15% chromium and 5% nickel, is heated to 3,000 degrees Fahrenheit and poured into the ceramic mold. This alloy is selected for its corrosion resistance and strength, making it ideal for marine applications. After the metal cools and solidifies, the ceramic shell is cracked open and the newly formed propeller is revealed. The gates and risers, which were necessary for metal flow during casting, are cut off, and the propeller undergoes a sandblasting process to remove any remaining shell material. The propeller then moves to the grinding operation, where skilled craftsmen refine the shape and ensure that it meets precise geometric specifications. The finishing process is critical to achieving the desired performance characteristics. The propeller is polished through a three-step process involving stone ceramic, synthetic plastic, and corncob treatments, followed by a final polishing with porcelain pins. The trailing edge of the propeller, crucial for hydrodynamic efficiency, is given a final grind. Finally, the propeller undergoes a 100% quality control inspection, where any necessary adjustments are made using hammers and anvils to meet Yamaha's stringent standards. Once approved, the propeller is packaged and ready for use, ensuring that it provides optimal performance for Yamaha outboard engines and contributes to an exceptional boating experience. Crankshaft machining on the Nakamura WT300 is a sophisticated process involving the use of a high-rigidity multitasking machine designed to perform both turning and milling operations with precision and efficiency. The Nakamura WT300, a product of collaborative engineering efforts, stands out due to its robust construction, advanced technology, and multitasking capabilities, making it ideal for complex machining tasks like crankshaft production. The WT300 is equipped with a high-rigidity boxway slide configuration on all axes, which ensures stability during the machining process. The machine structure is designed with a low center of gravity and a wide bed design, providing additional stability and reducing vibrations during heavy-duty operations. The box-type slides and guideways are high-frequency hardened and precision ground, ensuring long-term durability and accuracy. The traditional hand-scraping technique, known as kissage, used in the finishing of the slides, contributes to the machine's exceptional precision, continuing a legacy from the hydraulic lathe era. One of the key features of the WT300 is its ability to perform simultaneous cutting with upper and lower tools on the left and right opposing spindles. This multitasking capability allows for balanced processes and significantly faster cycle times. The machine is equipped with 2 turrets, each capable of holding up to 24 tools, providing a total of 48 tools that can be permanently available for various operations. This extensive tool capacity, combined with multi-tool holders and mid-position indexing of the turrets, greatly enhances the machine's flexibility and efficiency in machining complex components like crankshafts. The WT300 is powered by high-output motors that provide substantial cutting power. The left and right spindle motors offer 15/11 of a kilowatt of power, with up to 30 kilowatts available for turning shaft work with synchronized spindles. This high power enables the machine to handle the rigorous demands of crankshaft machining, which involves shaping the crankshaft from raw material through turning processes. The synchronized spindles ensure that the crankshaft is machined evenly and symmetrically, maintaining the necessary precision for this critical engine component. In addition to turning, The WT300 is also equipped with a milling tool motor that delivers 3.7 kilowatts of power. This allows for high-performance machining with small tools, enabling the machine to perform intricate milling operations required crankshaft manufacturing. The milling capability is further enhanced by the Y-axis movement on the turret, allowing for more complex geometries to be machined without repositioning the workpiece, thereby improving accuracy and reducing setup times. The WT300 is compatible with Nakamura's AGO Navi and Smart Pro AI technologies, which enhance the machine's capabilities through intelligent process monitoring and control. These systems assist in optimizing machining parameters in real time, ensuring consistent quality and reducing the likelihood of errors. The machine is also equipped with Smart Support, a feature that provides additional stability during machining, especially when working on long or slender components like crankshafts.